All right, so today we are going to introduce some properties of matter. The first thing that we're going to talk about today is density. What do we think of when we think of the word density? If we say an object is or is not dense, what do you think of? Good.
It's heavy or light.
Heavy or light. So we might think of, if I'm drawing a picture, if I say something is heavy, it might be a solid where the particles are really, really, really close together. But something like a liquid might be less dense and the particles might be kind of spread out. So if I'm just looking at if something's heavy or light. But if I'm looking as far as measuring density of some substances, what units do I use for density? Does anybody know that? Any of the two units that we would use? Okay, you use mass. So what do I measure mass in? Pounds. You can measure mass in pounds. If I'm using a balance, what is that normally measured in? Kilograms or grams. So if I measure the volume of something, if it's a solid, what units do I typically have? I would have something cubed, right? Like I would have like meters or centimeters cubed. But if I measure the volume of a liquid, like if it's a Coke, what is the volume of that? Milliliters or liters. So a hint for your activity is going to be that 1 milliliter is equal to 1 centimeter cubed. They're both volume, okay? So the unit that's cubed is equal to the unit of the volume that is in liquid. So here's going to be your formula for our lab activity, because we're going to calculate the density of these candy bars. So density is equal to your mass in grams over your volume. So this over sign, what does that mean? Divided by. Okay, so you're in your groups. What I'm going to ask you guys to do, I've given you the mass for the sake of time. Since we don't have balances in here, I've gone ahead and calculated the mass. So the mass of a Snickers, if you look on your worksheet, everybody can go ahead and grab that out with your partner. And go ahead and record the mass of the Snickers and the mass of the Three Musketeers bar. And be sure to note that it says to use your units. So it's in units of grams for our mass. Then once you're ready with your partner, go ahead and calculate your volume using the materials that you are given. You can unwrap them if you need to so it's more accurate. Use the materials that you were given to somehow calculate the volume of this solid object. And once you calculate the volume, as I walk around and monitor your work with your partner, go ahead and try to calculate the density using our formula. Does anybody have any questions? Volume of your candy bar. So you can unwrap it and just remember that with measurements, there's always that last digit of uncertainty. So just measure it to 2 decimal places. You guess on your last decimal place.
Oh, we're doing it.
Not good to just kind of. To find, aren't we doing length?
Yeah, what?
No, volume.
That's a good question. What side are we going to be using to measure? Are we measuring in inches or centimeters? Centimeters. And why? Because we said that 1 milliliter is equal to 1 centimeter cubed. That was our hint for our activity.
So length is 4, width is 2. Very.
2, just call it 2. Call it 2. We're gonna call it 1.6. Okay. That works.
12? No.
Okay, wait, what did you say the width was? The width was 2. 2. It's 2 by 4 by 1.6.
That's volume.
Just 4.
Right, I'm going to give you all 2 more minutes to calculate your volume. And once you calculate your volume, use our formula to go ahead and calculate the density of each of the bars. But then, what time am I on?
4.2 is the height.
What's the width?
I mean, the length. 4.2 by 2 times 1 is the length.
Oh, yeah.
I think you're.
14.28.
So it's the
That
same
makes sense.
thing.
That looks a lot bigger.
Boom.
Okay, you got your volume?
Yeah.
Okay, so using your volume, calculate density. So for density, what do you need?
You need mass.
You need mass and volume. Do you have those 2 units? Go ahead and calculate your density.
Okay.
And then
Mass.
this group. And then go ahead and continue on to test your observation.
What are we doing next?
We're calculating.
Go ahead and calculate density
So, mass divided by.
using your units, yeah.
1.3. I'm sorry. Math. Math today. Math is Okay. All right, so 15
1.42.
divided by 14.2. 1.05.
Okay, so you guys are ready for your next step?
Killing it.
All right, so you have your cup of water. And water's density is 1 gram per milliliter. So what you're going to do is you're going to see if each of your candy bars floats or sinks in water. So first you're going to predict, do you think they're going to float or sink? Are they heavier? Are they lighter than water, the density of water? So predict and give a reasoning.
And what's the density of water?
1 gram per milliliter.
This might float. This one's gonna sink. Ready? This one's definitely gonna sink. Bye-bye.
So be sure to explain, talk to each other and make sure you're explaining why you might think that it would float or sink.
This is more dense than water. Denser. Yeah, denser than water. Is that a word, denser?
Sure,
More dense.
more dense.
More dense. More dense. Do we need to pull these out of the water?
Justify it.
Yeah, pull it out before you test your next one, yeah.
I'm gonna need you to do that.
And then go ahead and continue on with some of your further questioning on the back side of your worksheet with your partner.
See what we predict. Yeah, let's just say what we think.
Okay.
What do you think?
I like halfway wasn't expecting that.
I thought it was 1 centimeter.
Why are we so fast?
1 milliliter is equal to 1 centimeter cubed. So whatever you calculate up here for your density, it's the same number,
Oh, it's saying.
same value.
So I bet it is
denser than
Don't know.
So the thinker thinks we'll get.
And if you're testing this, it might ask you why back here. Those are just some further questions. So continue on into the back side. Yeah.
So we got 1.05 for our density of the Three Musketeers, which could be like rounding error for us.
Yes.
So if something, if 2 things have the same density, what happens? Would it float or?
Well, since this is a liquid and it's a solid, it would be a little bit different. But usually, if something is the same or less than the density of water, it should float. So this one, it is a little bit heavier, but
Is that
But
why,
it's
like,
close
is that
enough.
why most of it is under the water?
yeah,
But
it
it's
does a
still
little
up
halfway.
here.
But if you look back here, it might ask you, why do you think? Or is that because of the makeup? Is it because it might be close to the same as water? So looking through those, try to explain why.
Okay.
Maybe it's because of its width interior.
Okay.
You know how it's light and fluffy
Disaster. Disaster. It was.
Three
It was.
Musketeers float.
And then the Snickers is, I'm gonna take this out now because other people have to do this.
Okay, I'm going to give you guys 1 more minute, and then we're going to try to relate this concept to chemicals.
1 more minute.
1 more minute.
And you want us to be done with this worksheet by then?
Yeah, or just at least discussing it.
I would say because the inside weighs more, assumptions.
It has more mass. Because the mass is
Might too.
It has air bubbles in it. This is straight carbon, no air.
What's the difference between the appearance?
What's the
I
difference?
think it has more to do with like the makeup of the inside, because if you think of like the inside of the Snickers, it's got like peanuts and caramel, and
Right,
those are really
makes it
dense
heavier.
things, and so it's like, meh.
Because they look the same.
Yeah, but I think it has to do with
The
what's on the
insides are
inside.
different.
That the makeup has something to do with the
Yeah.
density? That could be.
Yeah, that whipped fluffy center.
Okay, so as we're coming to an end point with our worksheet, if you're not completely done, it's okay. I just wanted to bring it all together before we end today's lesson to say that this is candy, right? But this is the process of how we might find density whenever we're using chemicals, their compounds, the elements. So as an exit ticket, we're going to use the same process to calculate density. We're going to use the same formula, mass over volume. But here, for your exit ticket, I've given you the density of a substance. I say substance instead of Snickers. So we could say the density of the Snickers is 1.63 grams per milliliter. If I have the volume of 25 milliliters, what is going to be my mass of the substance? I have this formula. How can I rearrange? I use density and volume. How can I calculate my mass? So work on that with your partner. And we're going to put that in our Dropbox on the way out the door. And then in our further lessons, we're going to talk about the periodic table, how the elements can be used from the periodic table, how we find our mass from the periodic table, and we're going to explore further properties of matter. Does anybody have any questions before we end today? You multiply. Yes, and then as you're ending your exit ticket, go ahead and put everything back in the bucket, and you can eat your candy.
I don't know if I want it.
You can have another one. Okay.
Start when you're ready, don't start.
Okay, so hi. Today we're going to learn about mitosis. Okay, so how many of you know anything about mitosis or what it is?
Remember the word?
Okay, it's good.
You know, they're connected to my feet.
Does that have something to do with like, who like this cells breaking apart? That's
Yes.
something completely different.
No, that's it. That's exactly it. Okay, so cells. Anybody know anything fun about cells they want to open up with?
Mitochondria is the powerhouse of
Nucleus is the brain.
Yes,
Yeah.
solid.
Difference between animal and plant.
Yeah, okay, nice. Okay, so what kind of cells are we made of? So we said plant, animal. What are we? Nice. Good answer. Okay, so your entire body is made up of cells, and they grow and divide, which help you grow and divide through a process called mitosis, as she mentioned. Like the cells, like dividing instead of breaking apart, because that's a different thing entirely. Okay, so what we're going to do today is work out with what has to happen in mitosis using fun materials. So I want you three to be a group, and you three are in a group. So grab some space, and you'll each get a little baggie of fun. Yes.
Wait, sorry. We're in a group.
Yeah.
Okay, packets.
Okay, so in your packet, you're going to find some blue string and some green string and some cutlery. Your blue is your cell membrane, your green is your nuclear membrane, and your knives, forks, and spoons are your chromosomes. So first step is to make a cell that has 6 chromosomes. And so basically your chromosomes are going to be what are called homologous pairs. So they'll be mostly the same but slightly different. So based on what you have for your chromosomes, your cutlery, how do you think that might happen?
It's like a big circle with all inside of it then?
Wait, ask that question one more
Okay,
time.
so based on your cutlery, if you're going to have 6 chromosomes with basically 2 pairs that are mostly the same but slightly different, how would that look?
Oh, there's pairs?
Yes, exactly it. So you have some forks that are different colors, so basically the same but slightly different. So, yes, perfect. And perfect. So I want you in your group to try and figure out how you get this cell into 2 identical daughter cells. Try and work through that process.
Daughter cells. Daughter cells is when it's split up into 2, right?
Yes.
Okay.
So you're going to go from this cell using your materials into 2 separate identical cells.
Okay, I can do that.
So green.
Separate identical
So blue should.
Separate, identical.
Yes, they're separate, but they're identical. They're the exact same.
They're
Oh, so I think it is like this.
Can I grab one too?
Yes, but others
Use
identical.
the rest of the stuff?
Uh-huh.
Ribosome.
Oh, okay.
Yeah, because as of now, those are not identical.
Right, okay.
Yeah. And as you do this, think about how a cell might have to do it. Like, so as a cell has internal mechanisms, think about how that cell might have to, do this on its own. So it can't just grab chromosomes and stick them in another cell. It has to go through a process of doing this. So think about how that might work.
Can we break the silverware? Is that what?
No.
Okay.
Please don't.
Okay, ask that question one more time.
Okay, so you're inside of all your cells, it has to do this within its little membrane. So you can't pick up cutlery, put them in a different cell. It has to do it internally and get them all divided as they should be.
Okay, so.
Oh, right, I'm
Are they
sorry.
supposed to be identical?
Yes. Because if they're not identical, then you have problems in your cells.
Wait, but these aren't identical.
I don't know what that means. I don't
It's not the
understand.
exact same on both sides.
Oh.
Are you doing it with just one or with both of them?
What do you think you have to do?
I'm not sure. Well, because it can't be equal.
Okay.
if we do-
Okay, so think about what chromosomes are made of, and know what chromosomes are made of.
Isn't that like a thing that defines if you're like male or female or something like that?
Part of them, yes. So your chromosomes are made of DNA. So DNA is what basically codes for you and who you are. And so DNA has to get to be the same in both cells. So if you have to go from one thing to two things that have to be the same, how would you do that? With all the materials you have.
We're not using the blue stuff? And this is different than this.
In theory, but it's hard to do on this. So that's your cell membrane, and this guy is your nuclear membrane.
Okay.
So the blue one's the one around everything else.
Yeah, I think the blue should be
Oh, so this
around
is
everything.
like the
The
entire thing.
massive one around everything else. Oh, so we kind of did split it inside of it.
Okay,
Okay.
okay. So it's split into two
And
dollars,
then,
which is this.
we can make,
And then we're supposed to,
So is there supposed to be 6 chromosomes or 6 pairs of chromosomes?
The original cell starts out with 6 chromosomes, so it has 3 different pairs of a knife and a fork and a spoon.
Okay.
And you have to end up with 2 cells that both have a pair of knives and a forks and a spoon.
There we go.
got it.
Okay, so
like we know what we're doing.
okay, so is everyone satisfied with their final product?
Yes.
Okay, so how did you get to where you did?
Okay, so this is the blue string is our, so this encompasses our whole. And so each of these are our nuclear membrane, and then they have to, I'm not sure why they're different colors though, but we have a pair of each of the different coloring in each of the nuclear membranes.
Okay, so how'd you get from 1 to 2?
I'm not sure.
Okay,
You split it into two, right?
okay, so where did the extra cutlery come from? Because the cell can't just go out and grab extra DNA.
It appeared.
So what might the cell have to do in order to go from, one green fork to 2 green forks?
Duplicate?
Yes, it's a duplicate. So in order for your cell to go from one cell to 2 exact copies, it must first duplicate its DNA. So you end up with what are called sister chromatids, which is a big fancy word for 2 exact copies. Okay?
So then if it were to, so if this one was like all by itself and it was split again and we were gonna do it, we would need like another set of like all the colors. Because
Yes,
it'd have to like duplicate itself.
exactly.
Oh,
Yay. Okay, so everyone understand how that process works? How the cell has to first replicate its DNA so then it can divide.
yes.
Okay, so and there are some nuances to this process. So one thing I didn't include for simplicity are things called centrioles and spindle fibers.
I've heard of those.
Okay,
I haven't heard of centrioles. I've heard it before.
Okay.
I can tell you what they do.
okay,
Is it the center of something?
not really.
So like this
It's worth a shot.
Spiral, never mind.
Okay, anybody else heard of centrioles or spindle fibers?
Spindles kind of sound like.
Connect stuff?
Yes, it does. Okay, so in your cell, as you are dividing and you have your little chromosomes hanging out, so if they're just chilling out like they are and they don't have, as you had hands to move them around, they have to have mechanisms with which to move the chromosomes around. Because if they just hang out like this and then the cell decides to divide, then you have messed up chromosomes.
Are the spindle fibers the like, when you see like a picture of mitosis, it's like the like lines like kind of pulling it apart?
Perfect. Yes. Yes. So you have to have spindle fibers that come along and attach to the middle of your chromosomes so they can then be pulled apart.
It's like tug of war.
Yes.
They duplicate or do they split? Or
They do both.
Oh.
Yeah.
So is it like they kind of like grow twice the size and then split?
That's exactly what happens.
That's
Okay.
cool.
Yeah. And so, yeah. So you actually have another lesson with Nicole to talk about the growth phase, which is super convenient.
So wait, what's the point of mitosis? Like why does that happen?
Well, okay, so like whenever you like first start out, your egg and sperm fertilized. If you don't duplicate, then you're going to stay that way forever.
Oh, okay.
Yeah.
Still like living and growing.
Yes.
Okay.
The
Yes.
reason why they grow and then split instead of just splitting and then kind of growing.
Because like, as the cell is before it duplicates, so it's just sort of hanging out with lots of little chromosomes and it's little bits inside the cell. So if it was just to divide these and then split, you'd end up with two really small cells that don't have all the stuff they need. So there's a lot of bits in the cells that like make your proteins and make your energy. So those have to be grown and divided as well, so the cell can split and then be functional. Any other questions? Okay. Anybody know? Okay, so when you started out, you had your cutlery in your nuclear membrane. Any ideas as to how that gets dealt with in the cell? Because if you just start out with your cell and your nucleus with your chromosomes in it, this can't divide and still divide a whole cell. Any ideas on what has to happen to that? Because if you just leave this as it is and the little spindle fibers, spindle fibers attached to the centrioles. It's important. So these little guys out here, they can't get in to get at their chromosomes. So what do you think has to happen to this guy?
Does it have to like disintegrate?
Yes. Yeah. So it has to disintegrate, and then after it goes through all the, lining up, coming apart, then the cell will then, like pinch in, and the nuclear membrane will reform, and the cells are happy again. And it's a great process.
So wait, is this the nuclear membrane? So like this would have to like disappear
Yes.
for it to split into two? Dope.
Yeah.
The nucleus is what contains itself.
Okay, so in the nucleus are just the chromosomes. Okay. So basically, whenever this disintegrates, all that happens is that the chromosomes are now free for the spindle fibers to find them and say, aha, yank them apart.
That's cool.
Yeah. So this is happening all day, every day, basically every 24 hours. Like your body cells do this. So like your skin will shed and has to get new skin cells, and like all your linings of your esophagus and your stomach. It's
So like
happening.
it's happening right now.
Oh yeah, all over your body.
That's
It's so great. Mitosis is awesome. Yeah. Any last final questions? I think I have like 10 seconds left. About mitosis? Okay. Thank you guys. You were great.
Today we're going to cover a little bit about genetics. On the board I have a starter for you. What I want you to do is I want you to list a few things, possible reasons for some of the genetic diversity found on our island. So what we've done is we have taken our little rowboat, sailboat, and we found this island. On this island, you have found dragon nests and dragons with large spade-like tails. You have found certain dragons with large wings. And then you found another set of dragons that have large horns and a thick skull. Each one of them, you can see sort of their nesting grounds. Just take a couple minutes here and try and come up with a few reasons why you might find the particular dragons where they are. You guys can talk to each other, it doesn't matter.
Can we ask questions about the drawing?
Sure.
The red where the spade tail dragon is?
It's a beach.
Okay, gotcha.
Beach.
Is that forest?
Yeah.
Okay.
This area is a forested area.
Yeah, they're ready.
Okay, let's talk about a few of your ideas. So, who has some ideas about why they might have some large spade-like tails?
To get through the sand?
Okay, so you.
Maybe to swim?
Okay, so we've got swimming or moving in the sand, right?
Digging.
Or if they fend off people or attack.
Defense?
Yeah, defense, that's what I was looking for.
Okay. So we've got a few things up there. What about our dragons with the large wings?
They can fly.
Yeah, they have to get up to
Okay, so for flight,
Strong winds and an updraft. Little wings won't do. You have to control.
okay. So coastal winds, right? Anything else? Okay. What about our dragons with large horns and a thick skull?
probably run into the trees a lot.
Okay.
Out of trees if I can shoot trees.
Okay, so
Hit the trees with their heads
Well, they can't fly to the top of
to
it.
get food.
so movement through thick bush.
Cave dwellers. Train up against rocks.
For food or for creating a home? Is that what I'm hearing? Is the reason that they're hitting their head in the cave is because they're making themselves a home, so they've dug in?
They break
Okay.
themselves in the gold down the door line.
So like smog. Okay. So what causes these things to sort of develop over time? Why do the dragons have these features?
Maybe because of where they live.
Okay, so you've got environmental factors, right? What else might cause these formations? So over years and years and years and years, what might happen?
Survival of the fittest.
Ah, I hear the word, survival of the fittest. Okay, so how does that end up happening? They end up replicating based off of, who's the strongest, who survives, who's able to get the most food, whoever is able to make the best home, whoever is able to make it to the tallest mountain, right? All of this is genetic displays. Over years and years and years, the genes have created these different aspects. So we're going to do a short little thing on the actual genes. So let's look specifically at our spade-tailed dragons. So you guys said that it's used for digging, swimming, creating holes kind of movement, right? So that genetic piece is going to be found on your chromosome, right? Got a little chromosome. For the sake of it, it doesn't really matter what chromosome this is. But you have things called alleles. So this tiny little section is an allele on this chromosome. And it specifically codes for the tail and how it's shaped. It just also happens to be that there are things called dominant and recessive traits, usually denoted by capital, lowercase letters. For this, the spade tail is now dominant. So this allele, the dominant, is spade tails. Recessive are straight. So this dragon specifically happens to be homozygous for the trait. So can anybody tell me what a homo usually means for in a scientific term? Same. So that means it has the same allele on both sets, right? It also happens to have the other alleles for wings and the horns. The alleles for those are both recessive, actually. So you have recessive on both of those. Can anybody tell me what this is? It has a specific name. Okay. This is actually called the genotype. So, keyword there, gene. What do the genes look like? Does that make sense? But we also have our phenotype, right? What does this look like? What does this actually look like? So we've already said it has a nice spade-like tail, no wings, no horns, right? Based off of our genome, or our genotype has tail, no wings, no horns. Okay. So this is picture, what it looks like, the picture. The P in phenotype can be remembered that way. What I'm going to ask you to do is I'm going to hand out some pieces of paper, and if you guys would work in pairs, you're going to make your own baby dragons. So what I want you guys to do, there is more than, okay. Actually, you guys can work on your own if you really, really want to. You guys are going to draw your own baby dragons using these features. So what I want you to do is make your baby dragon. Does it have wings? Does it not have wings? Does it have horns? Does it not have horns? Does it have a spade-like tail? Does it not have a spade-like tail? I want you to sort of draw out what that's going to look like, what your baby dragon should look like. Oh, that's perfectly fine.
Well, he's actually trying to get this out.
Oh my god.
What?
How to do it.
Are we not supposed to?
Can they have like just one thing of horns? Can you have like 5 horns?
It's just horns. They have large horns and a thick skull. So,
Be any?
yeah.
You never seen a dragon in real life?
No.
Okay.
Only one.
So, along with drawing them, I want you guys to give me a genotype and a phenotype. You're giving me the phenotype, so I want you guys to give me the genotype for your dragon. What does its genes look like?
So it looks like a demon.
Is that right? So he's got wings and he's got horns.
So are those,
He's got a tail.
okay, so when we said that they were recessive or dominant horns, the horns are dominant.
Okay.
Wings
so
are
that would be a
dominant.
capital H.
Mm-hmm.
Literally looks like a
How do
Just because when we're talking about the genes, those genes happen to be dominant because of the years that they've developed, they've become dominant. Okay.
I heard draw a dragon and just kind of like that.
Okay, and I need a genotype.
So if I wanted like thick skull with huge wings,
It's going to have at least one dominant, right?
okay.
Okay.
Wait, is this right? It has big horns, small wings, and a spade tail.
Okay, so if you're saying small wings, okay, I can see recessive.
Okay.
So
Okay.
small wings would be.
Could be recessive. Yes, it could be a recessive trait. Okay. So what we've covered what we've covered in this class so far is dominant recessive for Mendelian inheritance. Well, Mendelian inheritance. It's the simple version of genetics. What we would end up talking about next time are co-linked or incomplete dominance, like color.
Okay, guys, so what in the world is that? Have you ever seen one of those before?
No.
Never seen one of those before.
Is it a phase diagram?
It is a phase diagram. Way to go. Okay. So, what are the main phases of matter that we know? There are three.
Gas, liquid, solid.
Solid. So, let's say we got a beaker.
What do we have?
Here's the molecules of our solid. What else? Other two phases of matter.
Liquid.
Liquid. So the liquid's just hanging out in there. One more. Okay. So that's kind of what the molecules are going to look like in the different phases. Now the whole point of this phase diagram is to kind of show us where, given at a given temperature and pressure, what phase something's going to be in. So every thing, every compound, every element is going to have its own phase diagram. Okay, this is just a generic one. And the way I kind of like to remember it, solids on the left, where it's low temperature. Gas is on the right, where it's high temperature. And then liquids in that little cup up there. So that's the way I like to remember it. Okay. What do you call it when you go from solid to liquid? Like ice melting. Sorry, just gave that away.
Melting.
Melting. Way to go. What about when you go from liquid to gas? What's that called? Evaporation. What else? There's another word for it.
Vaporization.
Vaporization. There's another one starts with a B.
Boiling?
Yes. When you take water and you put it on a stove and you heat it up, it boils. What about when you go in the other direction? Condensation. What about when you go from a liquid to a solid? Freezing. When you go from a gas to a solid, it's called deposition, because you are literally depositing the gas onto a solid. What about when you go from a solid to a gas? Sublimation. That's weird. That's like dry ice. You ever seen dry ice? Oh, yeah. Yeah. Sublimation is dry ice. It's just sublimating everywhere. Because our temperature is down here. Or no, our temperature for the dry ice would be here. Our pressure is down here. So it would be over in here somewhere. So you got the solid dry ice, take it out of the cooler, it's going to go over here. It's not going to worry about the liquid, it's going to go straight to the gas. And it's really weird looking, it's really cool. I'll bring one of those in one of these days and let you guys see it. Okay. There is this guy right here. It's where all three phases meet. It's called the triple point. Why might that be?
Three things meeting. Triple.
You get all three phases at the same time. You've got a solid that wants to be a liquid, that wants to be a gas. So you get the gas, starts depositing, starts melting, starts liquefying. It's like it wants to be all three, but it can't pick, so it just goes back and forth. Right?
Is that what the superfluid means?
That's the next thing we're about to talk about. See that up there at the top on the far right? What's that say?
Critical point.
Critical point. That is the point at which there is so much temperature that the pressure can't hold it down anymore. There's enough pressure to make it a liquid, but it can't be a liquid anymore. It's too energetic. So it becomes this weird thing called a supercritical fluid. Yeah. Temperature goes up, then what happens to the molecules? They're always shaking, right? When you give them heat, what do? They shake harder. So if you take this solid, and you give it more energy, they're going to shake harder. So they're going to spread out. And if you take this and you give it more energy, they're going to start shooting off everywhere. Does that make sense? Cool. So past the critical point, you get this weird supercritical fluid that is half as dense as the liquid that it came from. So, to give you guys a little bit of practice with this, let's see. Pass those down, please. So, on our x-axis, you guys should be pretty good with axes, right? On our x-axis, we have our temperature. On our y-axis, we have our pressure. What's that pressure measured in? That's a weird little unit. What does it say?
Atmospheric pressure.
Atmospheric pressure. It's ATMs. Atmospheres it means that at sea level, it's the amount of air that is pushing down on you. Right? So you always have a big column of air on top of you all the time. At sea level, that's 1 atmosphere of pressure pushing down on you. So that's like right where we are now. A little bit. We're a little bit less because we're higher than sea level, but yeah, close enough. Okay. So, hello. I'm getting a phone call. What is the critical temperature of compound X? So how would we find that? Critical temperature, that's critical point. Around where would that be in relation to this phase diagram?
750, 760.
Yeah, about 750, 760 degrees Celsius. If you were to have a bottle containing compound X in your closet, what phase would it probably be in? What atmosphere or what pressure would your closet probably be in? Okay. So, the amount of pressure on you right now is about 1 ATM. So about 1 atmosphere. You have 1 atmosphere on top of you right now. So, in your closet, it's going to be what? Yeah. Probably a gas. Do you know what your temperature in your closet is?
Probably between 0 and 100 degrees Celsius.
It is definitely between 0 and 100 degrees Celsius. So you're safe. You're safe. Okay, at what temperature and pressure will all 3 phases coexist, you think? Around where?
350 degrees Celsius.
Yeah, about 350 degrees Celsius and what temperature, or what pressure?
50.
Around 50. Okay. If I take a bottle of compound X, this mysterious compound X, and I put it at a pressure of about 45 ATMs and a temperature of 100 degrees Celsius, what will happen if I raise the temperature to 400? You start at 45, so let's go up to 45, and your temperature is at 100. If I go from 100, on the x-axis, if I go from 100 to 400, what phase is it going to change from?
Solid to a gas.
Solid to a gas, which is called sublimation. Sublimation. What we say the reverse of sublimation was? Deposition. Cool. Why couldn't the compound be boiled at a temperature of 200?
It's already a gas.
It would be either a
Well-
solid or a gas.
Yeah, so let's go to 200 on the x-axis. No matter how high you put that pressure, it's always going to be a solid or a gas. It can never be a liquid at that pressure or at that temperature. If I wanted to, could I drink Compound X?
You'd die.
You probably
Would you?
shouldn't.
Well, if it was a liquid, it'd be over 400 degrees Celsius.
What's a
Yeah, but
gas?
it's not a liquid. Because
So you get inhale it, right?
So
Wait.
what atmosphere or what pressure are you at right now?
Just one.
1. So you're at the very bottom, right? And if you wanted to make it a liquid, what would you have to do to it? You'd have to raise what? And the temperature. So you'd have to go at least to 50 atmospheres and at least, what, about 350 degrees Celsius?
Right.
So, I mean, I guess you could.
Question.
Yes.
So temperature, is that the temperature of compound X or is it the temperature around compound X?
That's the temperature around Compound X that, it's the temperature that you bring the Compound X to.
Okay, so
Yeah.
my estimation that you would die if it was a liquid, because if you tried drinking something that was 400 degrees,
Then you would definitely, you'd have to,
some serious third.
You'd be
degree
hurting.
Right, like
you'd be hurting.
there's a good chance you would survive that.
Yeah, I don't imagine you could.
Yeah.
So we wouldn't want to take a shower in compound.
You definitely would not want to take a shower in Compound X.
That sounds creepy. Could we eat compound X?
Could you?
And we'd have to go to ridiculous pressure.
We'd have to go to ridiculous pressure.
In a normal situation,
Maybe like in the ocean you could eat
So-
Compound X.
we could smell it. Can we sniff it?
Could you sniff it?
We could.
You could waft it. You could waft it.
That's right. Science term. You don't sniff in science.
You don't smell, you don't sniff, you waft. Okay. So, to wrap up, I want you guys to review this, and we will practice a little bit with it tomorrow. Okay, what's your question?
What happens above 90 atmospheric pressures?
Above 90 atmospheric pressures,
Continue like blind or still go?
yeah, pretty much. And then if you increase the temperature, then you get the supercritical fluid.
Wow.
Okay? We good? Cool.